Alright, if you have not done so already, you can pick up your graded quizzes in the table, on the table in the back. The quiz has 30 points possible, so if you answered all of them correctly, you will get 30 points. In the grade book, I grade out of 25, just as a way to boost everyone's grade. So if you got all 30 points correct, in the grade book it would go down as 120%, which is, in my opinion, very generous. So your grade is out of 25 points, but don't be deceived by that. If you scored 20 points on your quiz, 20 out of 25 is technically 80%, but there was actually 30 points possible on the quiz, so 20 out of 30 would be closer to 67%. So I would say, for your own purposes, divide by 30 to get an idea of how you did on the quiz, but then take comfort in knowing that the grade in the grade book is divided by 25. Okay? If you have any questions on the scoring, after every answer box there is a small number in brackets, in square brackets. That's the point value of each question. Okay, so some questions were worth 4 points, other questions were worth only 1 point. I tried to indicate how many points you lost if you got partial credit. Otherwise, if you just see an X through it, just assume that you got 0 points for that question. If you got partial credit, I would have indicated how many points you lost. Okay. Yes?
Mr. Chairman, did you have to turn in a homework brief online? Write it up that I promised that I did the homework.
So the homework, you would, just as always, you would print that out and you turn in the paper in the table in the back. So I'm sorry, your question is?
There was on the first homework, there was this thing online where we have to go and we have to type up in a whole box saying I promise I did the homework, something like that, and submit it.
I don't ever remember. I don't remember anything like that. Okay. I'm really sorry. I don't know it. Okay. Yes.
So we have a quiz next week and the test the week after. How are we going to get our next week quiz back so we can study for those answers or something?
Okay, so that's a good question, and the answer is you won't get your quiz back until the day of the test. However, I will, during class time next week, I'll go over maybe some of the pressing questions from the quiz. So yeah, let me just talk about next week and the midterm, as those are coming up. So next week you will have a quiz. The quiz will cover chapters 4 and 5. Chapter 4 being the stuff on linear regression from last week. Chapter 5 is on probability, which we are covering today. You will have a quiz covering all of that. Then I will also cover chapter 6 after the quiz next week, and chapter 6 goes over the normal model. The midterm is the week after. On the day of the midterm, the first half of class, or I would say the first hour, is going to be a review session. So you will come here and I will take questions and answer them, kind of go over some concepts. You should have already been doing some studying, and so if you have any questions or topics that are still unclear or a little shaky on, the review session would be a good time to just make sure you become confident and solid on those topics. And then after the review session, we'll take the midterm. The midterm exam is an hour and a half, and so that will start around 8:30, and it will go until 10. Yes? The midterm has about 25 multiple choice questions and maybe 4 free response questions, kind of like the quiz. Okay, so there's 2 parts to the midterm exam. At least that's how I'm imagining it at this point. So yes, you will take a quiz next week. I will not have that graded until the week after, which is the day of the midterm. And so some of you will ask, how can we study off of this? So during class time, after you finish taking the quiz, I'll go over some of the topics that were covered. But beyond that, I won't be able to return the quiz to you and get that turned around that quickly. Okay? And I apologize for that, but that's just what happens when we meet only once a week in class. Yes.
The midterm, is it going to also have like what do we do? What do we do?
Yeah, so next week you get a note card. You can bring a 3x5 note card, writing on the front and back. For the midterm exam, I allow a 8.5 by 11 sheet of letter paper, writing only on one side for the midterm. For the final exam, I'll let you write on both sides. Okay. I'll talk about the midterm some more next week. There's already some information posted on the website about the midterm, covering topics that you should know, things to bring, all that stuff. Okay. All right. Questions, issues, comments before we get started on today's stuff? How's chapter 4? Linear regression, correlation, all of that?
Pretty easy.
Is it easy?
Pretty easy.
Okay. So when you take your quiz next week on, where part of it is on linear regression, we'll all get 100% on that section.
Just what I've learned from the homework, like the way they word it on the web, it's like you want to overthink it, but it's really not as much. You have to put so much thought into it. So really, they're asking for a direct question, direct thing, but it's like worded in just complicated way.
In general, try not to overthink things. That's a good principle for all of life, I would say. I try to ask my questions in a straightforward and fair way. Okay. If you have disagreements on the way I've written my questions, we can talk. But that's okay. All right, then we'll get started covering chapter 5. Probability. Is it just me, or are we missing a lot of people today?
Maybe they got scared of the first one.
Yeah. I'll take a look at the uncollected quizzes to see who's missing. All right, chapter 5, probability. So chapters 1 through 3 have all been all about data, describing data, summarizing data, even exploring relationships with data. So chapter 4 was exploring relationships between two numeric variables. In chapter 5, we're taking kind of maybe an aside or a slight detour into the land of probability. And probability is all about finding how likely or unlikely certain events are. It's different from data, all of the stuff where we've worked in chapters 1 through 4, because we're working more in theoretical ideas. Statistics always involves analysis of data and will always involve probability. It brings those two topics together so we can do our analysis, draw the conclusions from limited data. Okay? And so we need to have an understanding of probability in order to draw the conclusions. So probability those tools. Probability gives us tools to calculate how likely or unlikely an event or set of events are. by understanding the likelihood of events, I should say by understanding probability, we can see how likely it is so by understanding probability, we can see how likely it is for us to observe our data. And based on that likelihood, we can draw conclusions about our data. Drawing conclusions about data is what I argue is what statistics is all about. Okay. Okay, but before we can start drawing conclusions about data, we have to learn a bunch of ground rules of probability. So there's just a bunch of rules on how we calculate probabilities. And it's a little unfortunate that going over the rules of probability will seem a little boring, tedious, complicated for some. And it's not a whole lot of fun, I would say. Chapter 5 is probably going to be the least favorite chapter in our course. Just being honest with you. Maybe some of you will love it, but in general, this chapter is not as much fun just because there's a bunch of rules and theoretic ideas that we're kind of tossing around. So, anyway. So today we will learn all of these rules, okay? Learn the rules for calculating probabilities. So actually this week we learned the rules for calculating probabilities. Next week we're going to learn calculating probabilities for a certain model, which is important. And then the following week is the midterm, but then after that, that's when we can start drawing conclusions about data. Okay, so this week and next week, we're all in this land of probability, learning the rules for finding these probabilities. All right, so let's talk about randomness and probability. So we can calculate probabilities for random events. In this case, random means we are unable to predict the outcome. Unable to predict the outcome. However, if we study the random event, there's generally something we can understand about it. Okay, so we can still So for example, if I have a coin and I were to flip it, you would not be able to predict how it will land. You will not be able to tell me if it will land heads or if it will land tails. Okay. The best you can do is guess. That doesn't mean we can't understand how a coin flip works. Okay. We can understand very much that the probability that the coin lands heads is 50%. Okay. So we cannot predict the outcome of a single coin flip. We can, however, we can say that the probability that a coin lands heads is 0.50, 50%. Okay, so when we write this in terms of probability, we would write P coin lands heads is equal to 0.5. So P with parentheses indicates the probability of a coin landing heads is equal to 0.5. Sometimes you would see it written with PR rather than P. They are interchangeable. Okay, so I could also write P heads. What does it mean to say that the probability that a coin lands heads is equal to 0.5? What does that mean? Yeah.
That means there's a 50% chance that either it's going to land heads or tails.
Okay, so what does it mean for there to be a 50% chance that it lands heads? One more. Yeah. That half of the time it will land on heads. Is that true? If I flip a coin 10 times, will it land heads 5 times?
Not exactly, but there's a strong possibility.
Okay.
Does it have two sides?
It has 2 sides. That's
Well, the whole
No.
coin is 100%.
Huh?
It's 50 of it.
okay. All right. So the closest to the answer is that we can expect that the coin to land heads half the time. Although we know that's not true. I can flip the coin 4 times and it will not necessarily land heads 2 out of those 4 times. And if I flip the coin 3 times, it would be impossible to see half the time heads. I might have 2 heads, or I might have 1 head, or I might have 0 heads or 3 heads. None of those would actually be 50% heads. So what does it mean for the probability to be 0.5? Well, probability in this case refers to the long run relative frequency. The long run relative frequency. This is talking about if I were to flip the coin thousands of times or millions of times, and I were to keep track of how many times I flipped the coin and how many times it landed heads, then the relative frequency of heads to the total number of flips will be close to 0.5. So if I flip the coin 1,000 times, so for example, maybe it lands heads 508 times. So my relative frequency for heads and we remember relative frequency, right? Okay. So my relative frequency would be 508 divided by 1,000 or 0.508. This is not exactly 0.5, but it's close. And if I were to flip the coin 10,000 times or 100,000 times, we can expect my relative frequency to get closer and closer to 0.5. So when I say the probability that a coin lands heads is 0.5, that's talking about the long run relative frequency, meaning I flip the coin millions or billions of times. And what is the relative frequency it landed heads? That should be 0.5 in the long, long run. Probability of heads equals 0.5 means that in the long run being a million or billion or infinitely many coin flips, the relative frequency of heads should be 0.5. So here we make an important distinction between empirical probabilities and theoretic probabilities. Okay, what does the word empirical mean? Yes, go ahead.
The smallest like value or something? Like the lowest type of value?
Build up.
Okay. Maybe that's an alternate definition of empirical.
The most
But not-
reduced form of it?
Yeah.
Is it in terms of things you could think they're a faction or something?
Okay, so empirical means based on evidence, or in our case, based on data. Okay, so these would be probabilities based on evidence or based on data. So we use empirical probabilities many times. We would probably not use it for flipping a coin because we know that the probability that a coin lands heads is 0.5, but we could. If we were an alien from another planet, we've never seen a coin before, we don't understand how the laws of physics on Earth work, and somebody said, what's the probability that a coin should land heads? And if we have no idea, we could do an experiment ourselves. And we could just flip the coin 1,000 times and count how many times it landed heads, just like we did here. Okay, if we flip the coin 1,000 times, maybe after 1,000 coin flips, it landed heads 508 times. So if this is my first encounter with a coin, or whatever it might be, so far my empirical probability for how often will a coin land heads would be 0.508. Okay, because this is based off of the data or the evidence that I observed. So after 1,000 coin flips, and seeing 508 heads, the empirical probability of heads is equal to 508 divided by 1,000, or 0.508. Is that clear? Theoretic probabilities, on the other hand, these probabilities are based on mathematical rules or properties of the random event we studied. So for example, when we're talking about a coin, we would say a coin has two sides, heads and tails, and each side is equally likely to appear. Therefore, the probability a coin lands heads is 1 out of 2.5. So, in today's class, we're mostly going to focus on the rules for finding theoretic properties, or theoretic probabilities. But that's not to say empirical probabilities are not useful. In fact, for complicated events, there might be random events where finding the theoretic probabilities gets too complicated. Maybe the mathematical rules just get too complicated for us to find the theoretic probabilities directly. So in those cases, we will calculate empirical probabilities. Oftentimes we will set up a simulation on the computer, and we will have the computer run through thousands or millions of simulations, and based on those million simulations, we get an empirical probability. That should be a pretty good estimate of the theoretic probability. Is that concept okay with you guys? Alright, but today we will focus mostly on the rules behind theoretic probabilities. Okay, so let's start off with events with simple outcomes. Okay, so rules for finding theoretic probabilities. We have events with simple outcomes means every outcome is equally likely. So examples of random events with simple outcomes: flipping a coin. And the two outcomes are heads and tails. And both of those outcomes are equally likely. So this is an example of an event with simple outcomes. Another example: rolling a die. So when you roll a die, you can get, so die is singular of dice. You can get the face 1, 2, 3, 4, 5, or 6, and each of those faces are equally likely, so that would be another example of a simple outcome. Or we can draw a random card from a deck. Okay. And each of the 52 cards are equally likely. Okay, so then we can ask about certain events. Okay, so if we can define an event. So let's define an event A, and for simple outcomes, the probability that A will happen. Okay, so this we read as the probability of A. This is different from A itself. A is the event, and PRA or P of A is the probability that A will happen. Okay? Probability that A will happen, where A is the event itself. Okay. So we could say A is equal to the coin lands heads, and probability of A would then be 0.5. And it's important that we make this distinction because it would be wrong to write A equals 0.5. This is not correct. A is the event that the coin lands heads, and what we're talking about is the probability of A. Okay, so A is the outcome for a simple, a random event with simple outcomes. The probability of A is defined as the number of outcomes included in A divided by the total number of outcomes. So the probability of A, okay, is equal to the number of simple outcomes in A divided by total number of outcomes. So I could ask the question, I roll a die, what is the probability I get a number bigger than 1? Okay. So the event here, if we call A is getting a number bigger than 1. Okay? So which outcomes are part of this event? That would be 2, 3, 4, 5, and 6. Each of those numbers are bigger than 1, and those are all the outcomes included as part of that event. So how many outcomes, simple outcomes, are in A? 5 outcomes. So the probability of A would be 5 divided by 6. That's a probability of getting a number bigger than 1 if we roll it out. Is that okay? Alright, so try this out. Are you guys all familiar with a deck of cards?
Yes.
No.
Yes.
Yes? Okay, in a deck of cards, you have the ace, 2, 3, you have the ace through king, so it goes ace and then 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, and you have this sequence of numbers in 4 suits, which are hearts, spades, diamonds, and clubs. Total of 52 cards. The jack, queen, and king are considered face cards. The ace is not a face card. There's no face on the ace. So, these are considered face cards. So what if I ask, what is the probability of drawing a face card? Okay, so don't shout out your answer. Take a second to think about this. Sure. Okay, do we all have an answer? Yeah? Okay, and what is that answer?
23.8%.
12 over
12 out of 52. We have 12 face cards, the jack, queen, and king in 4 suits. So a total of 12 cards out of 52 cards total. If we turn that into a percentage, that would be something else, but this is fine. We can leave it in fractional form. I hope we're all okay with fractions.
Yeah.
Okay. Some of you are probably rusty, but I'm going to treat you all as if you are able to handle fractions. Yes.
So on the quiz, should we leave it in fraction form or could we change it to the?
Either form is acceptable.
Okay.
Okay.
You want us to simplify it or just leave it the way it is?
Yeah, you can leave it. You can simplify it. It's all the same. Okay. We have to be careful though. Sometimes, if we're not dealing with simple outcomes, meaning the outcomes may not all be equally likely. Okay. The outcomes are not always equally likely, and in those cases you cannot treat them like simple outcomes. So for example, I could say, I rolled 2 dice and add up the 2 numbers, okay, or and add the faces. I could ask, what is the probability that the 2 dice add up to 9? So in this situation, when we think of the outcomes of rolling 2 dice and adding the faces, the outcomes for the sum of two faces are what? What's the smallest number you can get? If you add up two dice, the smallest number you can get is 2. And what's the biggest number you can get? 12. Okay, and we can get everything in between. However, it would be wrong to say that each of these sums are equally likely. If you've ever played Monopoly or Settlers of Catan or any type of game where you're rolling 2 dice, craps at the casino, you know that certain outcomes are much more likely. It's much more likely to get a 7 than to get 12. Okay? So it would be wrong to say, well, I'm looking to get 9, and that is one outcome out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible outcomes. So the answer is 1 out of 11. That is not the case. All right, so to solve this, what would we have to do? Okay. There are actually 36 possible outcomes when you roll 2 dice. If this is 1 die, you can get 1, 2, you can get 1 through 6 on 1 die, and you can get 1, 2, 3, 4, 5, and 6 on the other die. Okay, so there are 36 possible outcomes, and all 36 are equally likely. Okay, so if you roll 1 and 1, you would get a 2, and if you roll 1 and 2, you would get a 3, and so on and so forth. How many out of these 36 add up to 9? Okay, well there's the 6 and the 3, the 4 and the 5 and the 4, and the 3 and the 6. So there are 4 ways to roll a 9. Can you see that? You have a question?
Yeah, I got confused at first. I understand like how you got 36 because obviously it's 2 die.
Uh-huh.
Two dice.
Uh-huh.
Like how do you? I'm like so confused.
You're so confused right now?
Yeah. I'm like how did you?
Okay. Alright, well, this is mostly for illustration, but this is to show that, so if I list the outcomes this way, these outcomes are not equally likely.
Right.
Okay? So these outcomes over here are not equally likely. Meanwhile, I didn't fill out this entire chart because that would be too time consuming, but there are 36 outcomes listed here. Okay? In each of these 36 are equally likely.
Based off the chart that you.
So we're saying, let's say you have 2 dice, one is red and one is blue. Okay? The red die can go 1, 2, 3, 4, 5, or 6. Okay? And for each of those things, the blue die could go 1, 2, 3, 4, 5, or 6. So when the red die is 1, the blue die can be 1, 2, 3, 4, 5, 6. When the red die is 2, the blue die can be 1, 2, 3, 4, 5, 6. There's a total of 36 dice combinations. Each of those combinations are equally likely. And how many of those dice combinations add up to the number 9? Out of those 36, 4 of them add up to 9. So 4 out of 36 add to 9. So the probability of rolling 2 dice that add to 9 equal to 4 out of 36, or 1 out of 9. Okay. So we have to, if we're going to try to do this rule regarding simple outcomes, we have to make sure that the outcomes are equally likely. Alright, so some general rules.